In this video, we will give a circuit analysis method called nodal analysis. Nodal analysis is a systematic method to be able to analyze any electric circuit. To begin, we will review some circuit definitions that we have learned before. A node is a point in the circuit where one or more elements connect each other. For example, node A is connected to 3 elements, 1 voltage source and 2 resistors. Node B is connected to 3 resistors. Similarly, node D is connected to 3 resistors, node C to 4 resistors, and finally node E to 2 resistors and 1 voltage source. In nodal analysis, we will always choose a reference node. For example, in the circuit shown, we have chosen node E to be the reference node, and the voltage at this node will be taken to be 0. And all other voltages will be measured with respect to this reference node. We will give the definition of nodal voltage next. A nodal voltage is the voltage rise from the reference node to any other node. For example, the voltage rise from node E to node A is called VA, which will have the positive end towards node A and the negative end towards the reference node E. Similarly, the nodal voltage VB will be positive towards node B and negative towards the reference node E. The voltage VD will be similar, positive towards D, negative towards E, and VC the same. To summarize, all nodal voltages will be given with respect to the reference node E, with the positive end towards the node which defines that nodal voltage and the negative end towards the reference node. The nodal voltages will be the variables that we will use to write equations to be able to solve any circuit using nodal analysis. We will state nodal analysis method next, and it states that we write KCL equations at all nodes except the reference node using the nodal voltages as the unknown variables and using known element values. To repeat, nodal analysis is to write KCL equations at all nodes except the reference node using nodal voltages as the unknown variables and any other known element values that are given in the circuit. These are the key ideas that we will be using in nodal analysis. As an example, we will show the analysis of the following circuit. This circuit contains one independent current source of 5 amperes and a few resistors. It has 4 nodes, nodes A, B, C, and D. There is no reference node given in this circuit, so we are free to choose any node. We will choose node D as the reference node, and the voltage at node D will be taken to be 0. The nodal voltages will be VA, VB, and VC. And we will use these nodal voltages as the unknown variables for which we will solve using nodal analysis. To quickly review nodal analysis, we have to write KCL equations at all nodes except the reference node in terms of the nodal voltages and other known element values. We will begin by writing the KCL at node A, which has the current source and 2 resistors connected to it. The direction of the current source is given. We have no choice in the direction of current flowing through it. For the 2 resistors, we are free to choose any current direction, and we will choose the directions which are leaving node A through both those resistors. And following the passive sign convention, the polarity of the voltages for those resistors will be given as shown to match the current directions that we have chosen. Writing KCL at node A, we have the current 5 amperes entering node A, and the convention we will follow is that currents entering a node are given a negative sign, so we will write down minus 5 amperes. The current leaving through the 30 ohm resistor will be given a positive sign, and the current leaving node A through the 30 ohm resistor will be VA minus 0 volts, which is the voltage at the reference node D, divided by 30 ohms. Similarly, the current leaving through the 7.2 ohms will be given with a positive sign, and the current leaving through the 7.2 ohm resistor will be VA minus VB divided by 7.2 ohms. These are all the elements connected to node A, and so KCL will sum up to 0. Next, we will write KCL at node B. We have 3 resistors connected to node B, and we will assume that the current is leaving node B from all of these 3 resistors in the direction shown. Since we have taken the current to be leaving node B, all currents will be with the positive sign. The current leaving node B through the 7.2 ohm resistor will be VB minus VA over 7.2 ohms. Current leaving through the 64 ohm resistor will be VB over 64. And finally, the current leaving through the 6 ohm resistor will be VB minus VC divided by 6. And this will be equal to 0 to satisfy KCL. Finally, we will write KCL at node C. And once again, we will assume all currents are leaving node C such that they show up with a positive sign. And KCL will give us that VC minus VB divided by 6 is the current leaving node C through the 6 ohm resistor, plus VC divided by 10 is equal to 0 to satisfy KCL. We have ended up with 3 equations in 3 unknowns, which can be solved for the unknown values VA, VB, VC. We will not go through all the steps to show you how to solve these 3 equations. We will leave that as an exercise for you to try. The solution of these 3 equations will give us VA is 60 volts, VB is 38.4 volts, and VC is equal to 24 volts. Once we have solved for the nodal voltages, we can calculate any other voltage or current in the circuit. For example, if you're interested in the voltage across the 6 ohm resistor, shown as Vx with the polarity given, then Vx will be equal to VB, the positive end of Vx, minus Vc, the negative end of Vx, which will be equal to 38.4 minus 24 is equal to 14.4 volts. The current through the 6 ohm resistor in the direction shown will be equal to simply Vx over 6 ohms is equal to 14.4 over 6, 2.4 amperes. To summarize nodal analysis for this circuit, we began by choosing a reference node, D. The nodal voltages that are unknowns will be VA, VB, and VC. Next, we wrote KCL equations at all the nodes except for the reference node in terms of the nodal voltages and other known values given in the circuit. We solved these equations for the unknowns and then calculated any other voltage or current needed in this circuit.